Hi everybody, welcome back. This is lesson 26, the inverse Laplace transform. And we're going to start in this video by just doing a little review of the material we covered last time, which is taking the Laplace transform. And then we're going to go to the inverse Laplace transform, which is like working backwards. So first, let's remember how to take the Laplace transform of a function. I will not go over the definition of Laplace transform, but I will remind you that when you start with a function, for example, a function f of t, then the Laplace transform of that will be a different function. We usually denote it with a capital rather than a lowercase letter. So if your original function is a little f of t, then the Laplace transform will be a capital F function. And the variable changes as well. It changes from t to s. So it will go from little f of t to capital F of s. And in addition, we're going to do this example, which has a few different Laplace transforms for us to try. And while we do that, we're going to refer to this table of Laplace transforms here. And there's also a link to this table in the lesson, so it's just something to keep kind of handy and with you as you work through this. Let's go ahead and get started. So, let's just take a look at number one. Find the Laplace transform, that's like this script capital L, of the function t squared plus 4t cubed minus 7t to the 6. Now, the nice thing about Laplace transforms is they obey this principle called linearity, and that means that when you're taking the Laplace transform that consists of a bunch of terms added or subtracted, you can split it up into the Laplace transform of each term. And if those terms have a constant in the front, you can put that constant in front of the Laplace transform. So it looks something like this. We're just going to call this, splitting it up, the Laplace transform of the function t squared plus 4 times the Laplace transform of the function t cubed minus 7 times the Laplace transform of t to the power 6. And now we need to apply the Laplace transform to each of these basic functions, and for that we're going to look at the table. Each of the functions we're taking the Laplace transform of is t to a power. So over in our table, here, if we look down, these are the different functions, and these are their Laplace transforms. And the function under t to the power n, where n is a positive integer, such a function has Laplace transform n factorial over s to the power n plus 1, where s is restricted to be greater than 0. So, in the first case, the Laplace transform of t squared, here the power n is 2. So when we plug it in, we're going to get 2 factorial over the power of over s to the power 2 plus 1, or over s to the power 3. So this one is equal to 2 factorial over s to the power 3. And here we need to keep track that s is got to be greater than 0. I'll add that over at the end. We may get other restrictions on our s variable, and we'll combine those all together at the end. All right, continuing, then we have plus 4, just copying from the line above, and now the Laplace transform of t cubed. Now, t cubed, we're going to use the same formula. T to the power n, we do n factorial, 3 factorial, over s to the n plus 1, so that's s to the 4. Continuing on, copying from the above line, we have minus 7, and then this one is t to the 6, and so we're going to have a 6 factorial over s to the 7. Now, for each of these, here and here, the restriction is also s greater than 0, so that's my total restriction there. I could leave it like this, but I can also simplify it just a little bit by multiplying out those factorials. I'm going to go ahead and do that. So we get here 2 factorial is just a 2 over s cubed plus 3 factorial is 6, and we can multiply that by the 4 that is in the front. 6 times 4 is 24 over s to the 4. And then finally, 6 factorial, well, we have to be a little bit careful there. It's 6 times 5 times 4 times 3 times 2 times 1. You, of course, can work that out on a calculator, or you can do it in your head if you wish. Let me see. 6 factorial. I get 720. Oh, however, that 6 factorial is multiplied by negative 7. So I need to take that 720, multiply by negative 7. And then I get negative 5,040. So I'm going to say minus 5040 over s to the 7. And here we have this restriction, s has got to be bigger than 0. Okay. That's the solution to our first example, the Laplace transform of t squared plus 4t cubed minus 7t to the 6th. Here, let's number this so that we're keeping it straight. Okay. What I would strongly recommend that you do at this point is pause the video, work through the other 3 examples here, problems 2, 3, and 4. I'll zoom into them on the page. If you want to pause the video, you can get them that way. Work them through, try to find the Laplace transform, and then come back and check your work. Okay, welcome back. We're going to go ahead and work through these. Problem number 2, find the Laplace transform of sine of t minus cosine of 3t. And using the what we call linearity, we can break this up because it's 2 things added or subtracted. So this is going to give us the Laplace transform of sine t minus the Laplace transform of cosine of 3t. Now, we need to apply the Laplace transform to each of these. Let's go ahead and see. Here, sine of at. Well, here, the a, it's like the coefficient in front of the t inside there, and it's just a 1. So in this problem, the a that we're looking at is 1. And the Laplace transform is the following formula. It is a over s squared plus a squared. Now we're going to substitute in 1 for the a, and then the s squared will just be s squared. And this is s larger than 0. So this is equal to 1 squared over, I'm sorry, it's just 1. It is not 1 squared, so I guess it doesn't make any difference in this case, but in another problem it could. So over s squared plus 1 squared. So it's a over s squared plus a squared. And for this one, s has to be bigger than 0. Okay, we now have minus the Laplace transform of cosine of 3t. So let's take a look at that one. Here, cosine of a number a times t. In this case, that number a is 3. So we have on the top the variable s. On the bottom, we have s squared plus a squared. And s is once again bigger than 0. So this will look like on the top here we have s. And on the bottom we have s squared plus 3 squared. And s is still bigger than 0, so I don't need to recopy that requirement. One more simplification step just to sort of pretty things up. This is 1 over s squared plus 1 minus s over s squared plus 9. And that is restricted to s being bigger than 0. Okay, so that's the Laplace transform of number 2, sine t plus cosine 3t. For number 3, let's go ahead, and once again, I encourage you to try it on your own first here. This is number 3, the Laplace transform of 5e to the 2t minus 4 sine 3t. And the first thing is we're going to split that thing up using linearity. So this is equal to 5 times the Laplace transform of e to the 2t. And then minus 4 times the Laplace transform of sine of 3t. Let's go ahead and look at our table to see what these Laplace transforms should be. This is a Laplace transform of e to a power t, but it's a power with a constant in front of it. So we're going to look for, in our table, for something of that form. And here we see the second row in the table, e to the power a number a times t. It's simply 1 over s minus a. In our case, that number a is 2, since this is e to the 2t. And so this is going to be, let me see, keeping the 5 from the front, this is going to be 1 over s minus 2. And here the restriction is that s is bigger not than 0, but bigger than a. So in this case, since a is 2, we're going to have s bigger than 2. All right, that takes care of our Laplace transform of our first term. Now we copy in that minus 4. And this is going to be the Laplace transform of sine of 3t. Now we saw that one before, or something similar to it, where the number involved, the number in front of the t, is 3. And let's just go and verify what it is. Sine of at is that number a, which is 3, over s squared plus a squared, and it's s bigger than 0. So it's equal to that number 3 over s squared plus a squared, and this has s bigger than 0. Let's just do just a tiny bit of simplification. I'm just going to move the numbers that are in front of the fractions up to the top of the fraction. So we have 5 over s minus 2. And then multiplying onto the top, it's going to be minus 12 over s squared plus 9. And then we want to combine these two conditions together. If we only want to look at numbers s, where s is bigger than 2, and also s is bigger than 0, well, combining those together, it's enough to look at ones where s is bigger than 2. Those are the ones we have to look at, because once it's bigger than 2, it's definitely bigger than 0. So this is our Laplace transform, and this is the interval on which it is defined. All right, let's take a look at number 4. Problem number 4 is the Laplace transform of 5t squared plus 3 sine 5t minus 2 e to the 6t cosine 2t. Okay, these things are getting more complicated along the way. That's to be expected. And let's give this one a shot. I'm going to go ahead and just paste a copy of it here so that I have it for reference. And then let's think about what is the Laplace transform of 5t squared plus 3 sine 5t minus 2 e to the 6t cosine 2t. Well, breaking that up using linearity, we have 5 times the Laplace transform of t squared plus 3 times the Laplace transform of sine 5t. And then this last term, because that e to the power and the cosine are connected by multiplication, linearity only gives us the ability to pull that constant out in the front, and we're going to have inside our Laplace transform this entire function. So it's going to look something like this, minus 2 times the Laplace transform of e to the 6t cosine 2t. Now, some of these we know already. I'm going to keep the 5. The Laplace transform of t squared, we'll just re-verify by looking at our table. This is t to the power n, and it's n factorial over s to the n minus, up over s to the n plus 1. So this one is 2 factorial over s to the 3. And we have a condition there, which is that s had better be bigger than 0. That came from that t to a power formula as well. Then we have plus 3 times the Laplace transform of sine of 5t. Now sine of at, sine of a constant times t, that's here, and it's equal to that constant a over s squared plus a squared, and it's once again s bigger than 0. So a over s squared plus a squared, where the a in this case is 5. So it's 5 over s squared plus 5 squared. And that, once again, is s bigger than 0. I don't need to add that on a second time. All right, now we're on to the last one, the one that's a little bit more complicated looking, minus 2 times, and this is a Laplace transform of e to a power with a number in front of the t, and cosine of a number in front of the t. So it's e to the 6t cosine of 2t. Let's see if we can find this. Unfortunately, we are not allowed to break up the Laplace transform into this times this. There's no nice rule like that. It's a little bit like doing rules for derivatives. When it comes to multiplication, you have to use something like the product rule. We don't have a product rule even for here. So looking in our table, we're looking for e to a power times cosine, and it looks like we have just such a thing here, e to the at cosine bt. Notice there are two constants to keep track of now, the one that's in the exponential function a and the one that's by the cosine b. And the form for that one looks like this. It's s minus a, where a is that in the power of the exponential function, over s minus a squared plus b squared. And the restriction is s is bigger than a. In our case, it's a matter of determining a and b. Our a is 6, and our b is 2. So this looks like s minus 6 over s minus 6 squared plus 2 squared. And this is s has got to be bigger than 6. That is bigger than a. Okay, this is our Laplace transform. I'm just going to do one more step in which we tidy things up a little bit. So 5 times 2 factorial, 2 factorial is 2, times 5 is 10. So this is 10 over s cubed. We have plus, multiplying the 3 times the 5 on the top, 15 over s squared plus 25. And then multiplying that negative 2 up on the top, I think it'll make our lives easier if we just keep it separate from the s minus 6, keep that factored out. 2 times s minus 6 over s minus 6 squared plus 4. Now, our two conditions that we have to meet both of are that s has to be both bigger than 0 and bigger than 6. And combining those together, it's all going to work when s is bigger than 6. Since that automatically means it's also bigger than 0. Okay, so here's our Laplace transform for this one. Of course, many more examples are possible. All of them rely on the table together with this linearity property, and you'll see some examples of those in the web work assignment from last time's lecture.